Right now, while you're watching this video, particles are racing through your body at 99.99999% the speed of light. Cosmic rays from distant supernovae are passing through you, through the walls of your home, through the entire planet, as if you're made of nothing but empty space. These particles are experiencing something you never will. They're touching the edge of reality's ultimate speed limit. And what they encounter at that threshold changes everything we think we know about space, time, and existence itself. For over a century, we've been told that nothing can travel at the speed of light. Einstein's famous speed limit, 219,792,458 meters per second. We treat it like a traffic law written into the fabric of the cosmos. But here's what makes this truly disturbing. It's not just that you can't reach light speed, it's that the universe will do everything in its power to prevent you from getting there. Mass will fight you. Time will abandon you. Space itself will conspire against your journey. The closer you get to that ultimate velocity, the stranger reality becomes, until at the final threshold, the universe reveals something so profound it changes what it means to exist. The numbers are staggering enough on their own. Light speed means crossing the distance from Earth to the Moon in 1.3 seconds, means circling our planet 7.5 times in a single heartbeat. It means that a beam of light could travel from Los Angeles to New York and back 40 times before you finish reading this sentence. But the raw speed is just the beginning of the story. What happens to you, to your body, to your perception of reality as you approach this cosmic boundary is something far more mind-bending than simply moving really, really fast. In 2011, scientists at CERN's Large Hadron Collider accelerated protons to 99.99991% the speed of light. At that velocity, those protons experience time 7,000 times slower than we do. A single second of their existence stretched to nearly 2 hours in our reference frame. They were touching something fundamental about the universe, something that Einstein first glimpsed in 1905 when he published his special theory of relativity. Since then, every experiment, every observation, every test we've conducted has confirmed the same impossible truth. The speed of light isn't just a speed limit. It's a fundamental property of reality itself, woven into the structure of space and time in ways that defy our everyday intuition. Tonight, we're going on a journey to that boundary. We're going to experience what would actually happen if you could somehow accelerate to light speed. Not the simplified version you've heard before, not the Hollywood fantasy. The real physics, the actual experience, the genuine cosmic horror and wonder of approaching a threshold that nature has decreed shall not be crossed. We'll discover why your mass would become infinite, why time would stop, why the universe would compress into a single blinding point of light ahead of you, and why the very concept of you might cease to have meaning at that ultimate velocity. This isn't just about speed, it's about the nature of reality itself. Because embedded in this speed limit is a profound truth about how the universe works, about the relationship between space and time, matter and energy, cause and effect. The speed of light is the universe's way of saying, this far and no further. And the reasons why are more fascinating than you could possibly imagine. As you're about to discover, the journey to light speed is a journey through increasingly bizarre physics. Each fraction of a percent closer to that ultimate velocity strips away another layer of familiar reality. At 50% light speed, things get weird. At 90%, they get bizarre. At 99%, the universe becomes unrecognizable. And at 100%, well, that's where the real story begins. Before we accelerate into the impossible, if you're fascinated by the hidden rules that govern our universe, subscribe and hit the thumbs up button. And here's something to consider. If you could travel at light speed for just 1 second from your perspective, how much time would pass for everyone else in the universe? Comment your answer below. I'll pin the most mind-bending response. We're going to build this understanding step by step, starting with what seems like a simple question. What happens when you first begin to accelerate? The answer involves something so fundamental that it will set the stage for everything that follows. Something about mass that Einstein realized changes the entire game. Now let's begin. Chapter 1: Infinite Mass. The moment you start accelerating toward light speed, something strange begins happening to your mass. Not your weight, not how heavy you feel, but your actual inertial mass, the fundamental property that determines how much force is required to accelerate you. And here's the disturbing part. The faster you go, the heavier you become, not by a little, by amounts that eventually approach infinity. This seems impossible. Your body hasn't changed. You haven't eaten anything. You haven't added any atoms to your physical structure. Yet according to Einstein's special relativity, confirmed by thousands of experiments over the past century, your mass is genuinely increasing. This isn't an illusion or a measurement error. It's a fundamental transformation in your relationship with space-time itself. The equation is deceptively simple. Your relativistic mass equals your rest mass divided by the square root of 1 minus your velocity, squared divided by the speed of light squared. At everyday speeds, this factor is negligibly close to 1. When you're driving at 60 miles per hour, your mass increases by roughly 1 part in 1,000 trillion. Completely unmeasurable, completely irrelevant. But as you approach light speed, that denominator shrinks towards 0 and the result explodes toward infinity. Let's make this concrete. Imagine you're sitting in a hypothetical spacecraft and you begin accelerating. At 10% light speed, about 30,000 kilometers per second, your mass has increased by just 0.5%. Barely noticeable. You'd need incredibly precise instruments to detect the change. At 50% light speed, your mass is now 15% greater than your rest mass. Still manageable, but now clearly significant. The engines pushing you forward have to work harder with each passing second, not just to increase your speed, but to move your increasingly massive body. At 90% light speed, something remarkable happens. Your mass has more than doubled. You now weigh more than twice what you did at rest, and every additional increment of speed requires exponentially more energy. But you're still only 9/10ths of the way to light speed. You have that final 10% to go, and that's where reality breaks down completely. Pushed to 99% light speed, and your mass is now 7 times greater than your rest mass. The spacecraft that started with you weighing, say, 70 kilograms is now hauling around the equivalent of 490 kilograms. But here's where it gets truly mind-bending. You still have that final 1% of light speed to achieve. That last 1% requires more energy than all the previous 99% combined. At 99.9% light speed, your mass is 22 times greater. At 99.99%, it's 70 times greater. At 99.9999%, your mass exceeds 700 times your rest mass. Notice the pattern. Each additional decimal place of precision, each tiny fraction closer to light speed, multiplies your mass by another factor. The universe is sending you a message. You cannot reach this boundary. In 2013, physicists at the relativistic heavy ion collider in New York accelerated gold ions to 99.9995% the speed of light. At that velocity, each gold ion had roughly 100 times its rest mass. The energy required to accelerate them, that final 0.005% to light speed, would have been equal to all the energy used in the previous acceleration. And to go from 99.9995% to actual light speed, infinite energy. Literally infinite. This is why nothing with mass can ever reach light speed. Not because we lack powerful enough engines or sophisticated enough technology, because the universe itself forbids it through the mathematics of space-time. As you approach light speed, your mass approaches infinity, which means the energy required to accelerate you further also approaches infinity. You'd need to harness more energy than exists in the entire observable universe just to push a single atom that final, infinitesimal distance to light speed. But here's what makes this even more fascinating. From your perspective inside the spacecraft, you feel completely normal. You don't feel heavier. Your body doesn't feel any different. You could step on a scale and it would read exactly what it always has. This mass increase is purely relativistic, only measurable from the perspective of the reference frame you're moving relative to. To external observers watching you pass by at near light speed, you've become monstrously massive. To yourself, you're unchanged. This creates one of relativity's most profound insights. There is no absolute reference frame. There's no universal perspective from which to measure speed, or mass, or time. Every observer's measurements are equally valid in their own reference frame. The universe doesn't have a preferred viewpoint. Your experience of unchanged mass is just as real as the external observer's measurement of your increased mass. Both are true simultaneously depending on where you're standing. Consider the implications for even trying to build a light-speed spacecraft. As you accelerate, you'd need progressively more fuel to generate progressively more thrust to move your progressively more massive ship. But the fuel itself would also become more massive, requiring even more fuel to move it, which would become more massive, requiring even more fuel in an endless, recursive nightmare. The tyranny of the rocket equation compounds with the tyranny of relativistic mass until the entire enterprise collapses into mathematical impossibility. Photons, particles of light, escape this trap through a loophole. They have no rest mass at all. Zero. Because they have no rest mass, they can travel at light speed without their mass becoming infinite. In fact, they must travel at light speed. They have no choice. Any particle with zero rest mass must always move at exactly light speed in all reference frames. Photons don't accelerate to light speed. They're born moving at light speed and can never slow down. They are light speed incarnate. This is the universe's first line of defense against your hypothetical light speed journey. Before you even worry about what you'd experience or perceive, you face an insurmountable barrier encoded into the fundamental structure of mass and energy. Your mass will rise without limit, requiring infinite energy to push through, and the journey ends before it truly begins. But let's imagine just for a moment that you somehow overcome this impossibility. Let's pretend you have access to infinite energy and can somehow continue accelerating despite your increasing mass. What happens next reveals something even stranger about the nature of reality itself. Because as your mass increases toward infinity, time itself begins to change. Chapter 2. Frozen Time. While your mass spirals toward infinity, something equally strange happens to time itself. Your clock begins to slow down. Not from your perspective, of course. To you, sitting in your spacecraft, your watch ticks normally. Your heart beats at its regular rhythm. Your thoughts flow at their usual pace. But to everyone you left behind watching from Earth, your time has slowed to a crawl. And the closer you get to light speed, the slower your time becomes, until at the ultimate threshold, your clock stops completely. This is time dilation, arguably the most unsettling consequence of special relativity. Time is not absolute. There is no universal clock ticking away the same seconds for everyone in the universe. Instead, time is relative, flowing at different rates for observers moving at different speeds. And the mathematics governing this flow are identical to the mathematics governing relativistic mass. The same equation that makes your mass increase also makes your time slow down. At 50% light speed, your time runs at about 87% the rate of Earth time. For every hour you experience, an hour and 9 minutes pass on Earth. Noticeable, but not dramatic. At 90% light speed, your time slows to 44% of Earth time. Your 1 hour equals 2 hours and 17 minutes back home. Now you're experiencing something profound. The universe is diverging into multiple time streams, and you've left the rest of humanity behind in the flow. At 99% light speed, the dilation factor reaches 7. Your single hour stretches to 7 hours on Earth. If you traveled at this speed for what feels like 1 year to you, 7 years would elapse for everyone you know. Your children would age 7 times faster than you. Your friends would grow old while you remained young. You'd return from a journey that felt like months to find decades have passed. This isn't science fiction speculation. This is observed, measured, verified reality. In 1971, physicists Joseph Heffel and Richard Keating flew atomic clocks around the world on commercial airliners. When they landed and compared the airborne clocks to identical clocks that remained on the ground, the flying clocks had indeed ticked slower by exactly the amount predicted by relativity. The difference was tiny, just a few hundred nanoseconds, because the aircraft's speed was minuscule compared to light speed. But the principle was proven. Moving clocks run slow. Since then, we've confirmed time dilation countless times. GPS satellites orbiting Earth experience time slightly faster than we do on the surface because they're moving quickly and in a weaker gravitational field. If we didn't account for relativistic time dilation in GPS calculations, your phone's navigation would be off by kilometers within minutes. The entire global positioning system is a practical, everyday technology that only works because we've incorporated Einstein's insights about the relativity of time. Particle accelerators provide even more dramatic confirmation. Moons are subatomic particles created when cosmic rays strike Earth's upper atmosphere. These particles are unstable with a half-life of just 2.2 microseconds. At rest, a moon would decay before traveling more than 660 meters. Yet moons created 10 kilometers high in the atmosphere regularly reach Earth's surface. How? They're traveling at 99.94% light speed, and from their perspective, they exist for their normal 2.2 microseconds. But from our perspective, their time has slowed by a factor of 29. Their 2.2 microseconds stretches to 64 microseconds in our reference frame, more than enough time to complete their 10-kilometer journey before decaying. Now push closer to light speed. At 99.9%, your time factor is 22. 1 year for you equals 22 years for Earth. At 99.99%, 1 year equals 70 years. At 99.9999%, 1 year equals 707 years. Do you see the pattern emerging? The same pattern we saw with mass. Each additional 9 in the percentage multiplies the time dilation factor by approximately 3. The closer you approach light speed, the more dramatic the divergence becomes. At 99.999999% light speed, time dilation reaches a factor of 2,236. If you spent what felt like a single day traveling at this velocity, 6 years would pass on Earth. A week-long journey from your perspective would span over 40 years back home. You'd return to find everyone you knew dead, your children elderly, your world transformed by decades of history you never experienced. And here's the truly disturbing implication. At exactly light speed, the dilation factor becomes infinite. Time stops completely. From the perspective of a photon traveling at light speed, 0 time elapses. A photon emitted from a star 1 billion light-years away reaches Earth instantaneously from its own perspective. It experiences no duration whatsoever between its creation and its absorption in your eye. The billion-year journey through space happens in precisely 0 time for the photon itself. This reveals something profound about light speed. It's not just the fastest possible velocity, it's the velocity at which time stops. Light speed is the boundary between time and timelessness, between duration and eternity. This is why you can never reach it, because reaching it would mean leaving time entirely, stepping outside the temporal dimension, into something else. And without time, causality breaks down. Without time, the very concept of traveling becomes meaningless. You'd need to exist in a before state and an after state, but without time, there is no before and after. Imagine the psychological reality of time dilation for a moment. You're in your spacecraft racing away from Earth at 99.99% light speed. You glance at your watch, 1 hour has passed. You look out the window at Earth, now far behind you, and somehow you can observe what's happening there. 70 hours have passed on Earth, nearly 3 days. You watch your family aging in fast forward. You see morning turn to night, turn to morning, turn to night, 70 times for every beat of your heart. This creates a fundamental asymmetry in the universe. You can travel into Earth's future, but you can never travel into your own future. From your perspective, you're always experiencing time, normally 1 second per second, but you're surfing along the timeline of the universe, jumping forward into the future of everyone else, and there's no way back. You cannot reverse time dilation. You cannot return to the temporal reference frame you left behind. The future you've jumped into becomes your new present, and it's permanent. This is why near light speed travel is fundamentally a one-way journey, not through space, but through time. You could visit a star 100 light years away and return to Earth, but if you traveled at 99.9999% light speed, you'd find that 140,000 years have passed on Earth during your subjective journey time of perhaps a few years. Everyone you knew would be long dead. Human civilization might not even exist anymore. You'd return as a time traveler from an ancient era, a fossil consciousness stepping into an unrecognizable future. In 2013, physicist Amos Ory at the Technion Institute calculated what he called the maximum practical speed for human space travel, considering the psychological effects of time dilation. He concluded that humans probably couldn't tolerate time dilation factors greater than about 10 without severe psychological trauma. That limits us to about 99.5% light speed at most. Beyond that, we'd be cutting ourselves off from our own species, exiling ourselves from human history. Yet time dilation is just one facet of what happens as you approach light speed. While your clock slows to a crawl from Earth's perspective, another even stranger transformation begins. The universe itself starts to change shape. Space, that seemingly empty void you're racing through, begins to compress, and what you see when you look out the window becomes something utterly alien. Chapter 3: Compressed Universe. As your velocity climbs toward light speed, the universe in front of you begins to shrink. The distance between you and your destination compresses, folding space itself like an accordion. This is length contraction, special relativity's third major effect, and it transforms the very geometry of the cosmos from your perspective. The mathematics are elegant and disturbing. Any object moving relative to you appears shortened along the direction of motion by exactly the same factor that governs time dilation and mass increase. At 50% light speed, distances ahead shrink to 87% of their rest length. At 90% light speed, they compress to 44%. At 99%, just 14% remains. The universe is collapsing. Consider a journey to Alpha Centauri, our nearest stellar neighbor, at 4.37 light-years away. From Earth's reference frame, this distance never changes. It's 437 light-years whether you're sitting still or racing toward it at 99% light speed. But from your perspective inside a spacecraft traveling at 99% light speed, Alpha Centauri is no longer 4.37 light-years away. Space itself has contracted. The distance is now just 0.61 light-years, about 1/7 its rest length. This creates an apparent paradox. Earth observers watch you travel 4.37 light-years at 99% light speed, which takes about 4.4 years of Earth time. But you experience significant time dilation, so your onboard clock shows only 0.62 years have passed. How can you travel 4.37 light-years in 0.62 years without exceeding light speed? The resolution. From your perspective, you only traveled 0.61 light-years. You traveled a shorter distance in less time, and your speed relative to the compressed space remains below light speed. The universe remains consistent by warping both space and time simultaneously. In 2008, scientists at the Brookhaven National Laboratory collided gold ions at 99.995% light speed. Sophisticated detectors measured the shape of these ions as they collided. Each gold nucleus, normally spherical and about 15 femtometers in diameter, appeared compressed to a pancake just 0.3 femtometers thick in the direction of motion, a 50-fold contraction. The ions were literally flattened by their velocity, transformed from spheres into disks so thin they were nearly two-dimensional. Now extrapolate this to your entire journey. As you accelerate toward light speed, not just your destination but the entire universe ahead of you compresses. At 99.9% light speed, the distance to Alpha Centauri shrinks to just 0.2 light-years. At 99.90%, it's a mere 0.6 light-years. At 99.999%, the entire 4.37 light-year journey compresses to less than 20 billion kilometers. That's roughly the diameter of our solar system. From your perspective, Alpha Centauri has moved to the edge of our solar system. Space has folded. This isn't an optical illusion. This isn't just what things look like from your perspective. This is actual physical contraction. From your reference frame, those distances have genuinely shortened. If you could somehow reach out and measure the space between you and your destination with a ruler, you'd measure these compressed distances. The universe has restructured itself around your motion. At exactly light speed, length contraction reaches its ultimate conclusion. The contraction factor becomes infinite. All distances in the direction of your motion shrink to exactly zero. From a photon's perspective, the entire universe along its path of travel has zero length. A photon traveling from one side of the observable universe to the other, spanning 93 billion light-years, experiences that journey as having zero distance. It's born at its source and arrives at its destination in the same instant, with no space traversed in between. For light, the universe is infinitely compressed. This reveals a profound complementarity with time dilation. Remember, photons experience zero time during their journey. Now we know they also experience zero distance. Time and space both vanish at light speed, not separately, but as a unified four-dimensional space-time. Einstein's great insight was that space and time are not independent entities. They're intertwined dimensions of a single continuum, and your motion through this continuum determines how much distance converts into duration and vice versa. Think about the implications for attempting near-light speed travel. From Earth's perspective, a journey to a star 1,000 light-years away takes at least 1,000 years at light speed, impossible for any human lifetime. But from your perspective, traveling at 99.99999% light speed, that distance contracts to just 14 light-years. With time dilation slowing your clock, you'd experience the entire journey in a subjective time of just 14 years. You could reach stars hundreds or even thousands of light-years away within a human lifetime from your own perspective. This creates a bizarre asymmetry. You undertake a 20-year journey from your perspective to a star 1,000 light-years from Earth. You turn around and return at the same near-light speed. Another 20 years subjective time. You've aged 40 years and expect to return to an Earth that's about 40 years older. Instead, you find that over 2,000 years have passed. Everyone you knew has been dead for millennia. Entire civilizations have risen and fallen. You've become a living fossil, a remnant of an ancient era, having skipped through the centuries in your compressed, time-dilated bubble of space-time. This is the infamous twin paradox, though it's not really a paradox at all, once you understand that acceleration breaks the symmetry. The twin who travels undergoes acceleration and deceleration, experiencing real forces that distinguish their reference frame from the stay-at-home twin's inertial frame. The traveling twin genuinely ages less, experiencing less time, traversing less distance, and this asymmetry is absolute and observable when they reunite. But length contraction reveals something even stranger when you consider what happens to objects perpendicular to your motion. Distances along your direction of travel compress, but distances perpendicular to your motion remain unchanged. A sphere moving past you at near light speed appears compressed into an ellipsoid, squashed along the direction of motion, but maintaining its width. The universe is developing a preferred direction, the direction you're moving. From your perspective, inside the spacecraft, looking forward, the universe appears compressed ahead of you. The stars are closer than they should be. Constellations are distorted, with stars along your flight path squeezed together, while stars to the sides maintain their separation. Behind you, the effect reverses. The universe you've left behind appears stretched, expanded, the distances you've already covered growing longer in your wake. At 99.999% light speed, you'd see the entire galaxy ahead of you compressed into a narrow band. If you were crossing our Milky Way's diameter of 100,000 light-years, from your perspective, you'd only be crossing about 1,400 light-years. The journey that would take 100,000 years at light speed from the galaxy is perspective, takes just 1/400 years of your subjective time. You're carving through space faster than light speed from your own measurements, except you're not. You're traveling through compressed space at sublight velocity. The universe accommodates your journey by transforming the geometry itself. This compression effect doesn't just apply to empty space. Everything physical compresses. If you were approaching Earth at near light speed, our planet would appear squashed along your direction of approach, transformed from a sphere into a flattened ellipsoid. Mountains would appear shorter in the direction of your motion. The atmosphere would compress into a thin film. At 99.99999% light speed, Earth would appear as a thin disk just 57 kilometers thick in your direction of travel, though still 12,442 kilometers wide perpendicular to it. The compression continues without limit as you approach light speed, creating an increasingly distorted, increasingly alien universe. But length contraction is just the beginning of how relativity transforms your perception. Because while space compresses and time dilates, something even more visually dramatic happens. The light reaching your eyes begins to behave in impossible ways, transforming the entire visible universe into a psychedelic nightmare of distorted colors and compressed stars. Chapter 4: Distorted Light. While length contraction reshapes the geometry of space, something equally bizarre happens to the light entering your eyes. Colors shift dramatically. Stars change hue. The familiar spectrum of visible light transforms into something alien. This is the relativistic Doppler effect, and at near light speeds, it renders the universe unrecognizable. You're probably familiar with the ordinary Doppler effect from everyday experience. An ambulance siren sounds higher pitched as it approaches, then lower as it recedes. Same phenomenon with light. Light from objects approaching you shifts toward higher frequencies toward blue. Light from receding objects shifts toward lower frequencies toward red. Astronomers use this effect to measure the velocities of distant galaxies. We call it redshift when galaxies move away from us, blue shift when they approach. But the relativistic Doppler shift operates on an entirely different scale. At ordinary velocities, the frequency shift is proportional to your velocity. At relativistic velocities, the shift becomes extreme, transforming not just the color, but the entire nature of the radiation you perceive. Imagine you're accelerating toward a distant star that emits yellow light at a frequency of about 520 terahertz. At rest, you'd see this star as yellow just as it appears from Earth. But as you accelerate, the light blue shifts. At 50% light speed, The frequency increases to about 900 terahertz. The yellow star now appears violet, shifted well into the blue end of the visible spectrum. At 90% light speed, the frequency reaches 2260 terahertz. The visible yellow light has blue shifted entirely out of the visible spectrum into ultraviolet. The star has vanished from sight, though UV detectors would show it blazing with invisible radiation. At 99% light speed, the blue shift becomes extreme. That yellow light now oscillates at 11,700 terahertz, deep into the ultraviolet range. At 99.9%, we're at 73,500 terahertz, approaching soft X-ray frequencies. The gentle yellow light from a sun-like star has transformed into penetrating X-ray radiation. If you look directly at this star, you wouldn't see yellow or blue or violet. You'd see nothing in visible light, but your body would be bathed in increasingly energetic electromagnetic radiation capable of damaging your DNA. This creates a profound problem for near-light speed travel. The universe ahead of you becomes progressively invisible in ordinary visible light while simultaneously becoming dangerous in high-energy radiation. Stars blue shift out of visibility. The cosmic microwave background, that faint radio whisper permeating all of space at a temperature of 2.7 Kelvin, blue shifts into visible light, then ultraviolet, then X-rays. At 99.99% light speed, even the cosmic microwave background radiation blue shifts to gamma-ray energies. The cold bath of photons left over from the Big Bang becomes a lethal flood of high-energy radiation that would fry any biological organism in seconds. In 2011, physicist William Edelstein at Johns Hopkins calculated the radiation exposure for astronauts traveling at 95% light speed. He found that interstellar hydrogen atoms, normally harmless, would blue shift to energies sufficient to create deadly particle showers when they collided with a spacecraft's hull. At these velocities, every proton in the thin interstellar medium becomes a cosmic ray. You'd need shielding comparable to the walls of a particle accelerator just to survive the empty space you're racing through. But blue shift ahead is only half the story. Behind you, light redshifts. Stars you've passed shift toward red, then infrared, then radio waves. The sun, receding behind you at 99% light speed, would appear as a dim red ember. At 99.9%, it would redshift entirely out of visible light into infrared. At 99.99999%, the sun's visible light would redshift to radio wavelengths, and our star would vanish from optical view, detectable only with radio telescopes. This creates an asymmetry in your perception. The universe ahead blue shifts toward higher energies and invisibility. The universe behind redshifts toward lower energies and darkness. At sufficient velocity, you'd be surrounded by an invisible cosmos, trapped in a narrow band of normal light that shrinks with every increment of speed. The relativistic Doppler effect combines with another phenomenon called aberration. Just as raindrops appear to come at an angle when you're driving, even if they're falling straight down, light appears to come from different directions when you're moving at relativistic speeds. Stars ahead of you appear to shift forward in your field of view, while stars to the sides also appear to move forward. The entire sky compresses into a shrinking circle ahead of you. At 50% light speed, stars 60 degrees to the side of your forward direction appear shifted to just 42 degrees. At 90%, those same stars appear at 15 degrees from straight ahead. At 99%, they're at just 5.7 degrees. The entire visible universe is collapsing into a tight cone directly in front of you, while the view behind you expands into emptiness. At 99.99999% light speed, aberration reaches its ultimate form. The entire celestial sphere, normally spanning 360 degrees around you, compresses into a tiny circle less than half a degree wide directly ahead. That's about the angular size of the full moon. Every star, every galaxy, every photon in the observable universe appears squeezed into a region the size of the moon as seen from Earth. Behind you, the view is almost completely black. The universe has collapsed into a tiny spotlight of compressed, blue-shifted radiation ahead and an empty void of red-shifted darkness behind. This creates a visual effect that's been rendered in several physics simulations. As you accelerate toward light speed, the familiar stars ahead don't simply get brighter and bluer. They stream toward the center of your forward view like falling into a tunnel. Stars from the sides rush forward, joining the compression. New stars that were behind you swing around into your forward view, though highly redshifted. The entire cosmos rotates around you, spiraling into a central point of intense, blue-shifted light. In 2010, students at the University of Tübingen in Germany created computer simulations showing what a near-light-speed journey through a city would look like. Buildings appeared stretched and distorted due to aberration. Colors shifted wildly. The field of view compressed dramatically. Most disturbing was the temporal distortion. Objects on one side of your view appeared at different moments in time due to the finite speed of light and your high velocity. You'd see the past and future of the same object simultaneously depending on its position relative to you. Combine Doppler shift, aberration, and length contraction, and you get a visual experience unlike anything possible at ordinary velocities. Stars compress into a narrow forward cone. Those ahead blue shift toward ultraviolet and X-rays. Those behind redshift toward infrared and radio. The familiar constellations distort beyond recognition. Distances appear compressed. And one more effect emerges: the intensity of light changes. Because light ahead of you blue shifts to higher frequencies, and because aberration concentrates more light into your forward field of view, the brightness of the universe ahead increases dramatically. That tiny, compressed circle of stars ahead of you is receiving not just the light from the stars directly in front, but blue-shifted, concentrated light from stars that would normally be to your sides and even behind you. It's as if the entire universe is pouring its light into a single focused beam aimed directly at your eyes. At 99.9999% light speed, the intensity of this forward light cone becomes almost incomprehensible. You're not just seeing stars ahead of you, you're seeing the integrated light of billions of stars, compressed, blue-shifted, concentrated into a circle the size of the moon. The intensity would be like staring directly at the surface of the sun, except worse, because it's not just visible light. It's gamma rays, X-rays, ultraviolet radiation, all compressed into that tiny aperture. This is what you'd actually see if you traveled at light speed, almost nothing in visible wavelengths. The universe would become a lethal, invisible tunnel of high-energy radiation ahead and a dark void of red-shifted nothingness behind. The visual experience that filmmakers love to depict, with stars stretching into lines, is wrong. The real experience would be profound darkness punctuated by a small, incredibly bright, increasingly invisible disk of deadly radiation straight ahead. You'd be racing through what appears to be an empty void toward a single point of concentrated cosmic energy. And this is just what reaches your eyes. What happens to your eyes themselves, to your brain, to your body's ability to process this information reveals another layer of impossibility in the light-speed journey. Because as space compresses, time dilates, and light distorts, your own biology begins to face challenges that go beyond physics and into the realm of survival. Chapter 5: Impossible Acceleration. Before you even worry about what you'd experience at light speed, there's a more fundamental question: how do you get there? The physics of acceleration toward light speed reveals why this journey is not just difficult, but genuinely impossible, even with unlimited energy at your disposal. Newton's second law says force equals mass times acceleration. Double the force, double the acceleration. Simple, intuitive, and completely wrong at relativistic speeds. As your velocity increases, your relativistic mass increases, requiring more force to achieve the same acceleration. But it's worse than that. The relationship isn't linear, it's exponential, asymptotic, approaching infinity. Let's make this concrete. Imagine a spacecraft with a rest mass of 1,000 kilograms, about the mass of a small car. You want to accelerate it to light speed. At low velocities, applying 1 Newton of force would accelerate this craft at 0.001 meters per second squared. Gentle, but it works. Maintain this force long enough and you'd eventually reach orbital velocity, escape velocity, even a significant fraction of light speed. But as you approach relativistic speeds, the same force produces less and less acceleration. At 50% light speed, that 1 Newton now produces only 0.075 meters per second squared acceleration. Your mass has effectively increased to about 1,300 kilograms from an external observer's perspective. At 90% light speed, the same force accelerates you at just 0.0119 meters per second squared. Your effective mass is now 4,600 kilograms. At 99% light speed, your 1 Newton of force produces a mere 0.2 meters per second squared of acceleration. Your mass has ballooned to 50,000 kilograms. You're applying the same force, but the universe's resistance has increased 50-fold. To maintain your original acceleration rate, you'd need to apply 50 times more force. And you're still only 99% of the way to light speed. That final 1% is where the exponential curve goes vertical. At 99.9%, you'd need 700 times your original force. At 99.99%, you'd need 7,000 times. At 99.9999%, you'd need 70,000 times the force just to maintain the same acceleration you had at rest. The universe is fighting you with increasing ferocity. In 2016, physicist Davis Gibbons at Albion College calculated what he called the relativistic rocket equation. He showed that to accelerate a 1,000 kilogram spacecraft to just 99% light speed using conventional rocket propulsion, you'd need a fuel-to-payload mass ratio of approximately 14 billion to 1. For every kilogram of spacecraft, you'd need 14 billion kilograms of fuel. To reach 99.9%, the ratio climbs to 1.3 trillion to 1. These numbers make the journey absurd before you even consider the energy requirements. But let us ignore fuel and imagine you have an antimatter drive or some hypothetical propulsion system with unlimited power. You still face the acceleration problem. Not the physics of mass and energy, but the biology of human survival. Because while your spacecraft accelerates, you experience force. And that force has to be transmitted through your body. Consider a modest acceleration rate, 1g, equivalent to Earth's gravity, or 9.8 meters per second squared. This is comfortable. You could sustain it indefinitely without harm. It's the acceleration fighter pilots experience when flying level, what astronauts experience on the launch pad before liftoff. At this rate, you'd reach 50% light speed in about 177 days. You'd reach 90% in about 320 days. This seems reasonable for a long interstellar voyage, but here's where relativity creates a cruel trap. From Earth's perspective, your acceleration rate decreases as your mass increases. At 1g of proper acceleration, which you feel as constant comfortable gravity, an external observer sees your rate of velocity increase, slowing dramatically as you approach light speed. After 1 year of accelerating at 1g from your perspective, you've reached about 77% light speed from Earth's perspective. After 2 years, you're at 97%. After 3 years, you're at 99.6%. After 10 years of constant 1g acceleration from your reference frame, you've reached 99.995% light speed from Earth's perspective, but you can never reach 100%. The asymptote is absolute. You could maintain 1g acceleration for 1,000,000 years from your perspective, constantly feeling comfortable artificial gravity from your engines, and you'd never reach light speed. You'd get asymptotically close, adding nines after the decimal point, indefinitely, but the final threshold remains forever out of reach. The universe simply won't let you cross it. Now imagine you want to reach light speed quickly within hours instead of years. This requires tremendous acceleration. To reach 90% light speed in 1 hour from your reference frame requires acceleration of about 760 gra. For 1 second, you'd weigh 760 times your normal weight. Your blood would pool, your organs would compress, your bones would shatter under their own weight. The maximum acceleration humans have survived is about 46 Gs for a fraction of a second. At 760 Gs sustained for an hour, you'd be crushed into paste against your seat within seconds. Even if you could somehow survive this acceleration, you face another problem: power requirements. These aren't engineering challenges, these are fundamental constraints imposed by the structure of space-time itself. The universe has established a maximum speed, and it enforces this limit through mechanisms that become exponentially more stringent the closer you approach it. Mass increases without bound, energy requirements approach infinity. Acceleration becomes impossible. But let's perform one final thought experiment. Suppose you somehow overcome all of this. Suppose you have infinite energy, indestructible materials, and a biology that can withstand any acceleration. You apply unlimited force to your spacecraft, cranking up the acceleration beyond any physical limit. What happens? The answer comes from the mathematics of special relativity. No matter how much force you apply, no matter how much energy you pour into your engines, your velocity approaches light speed asymptotically, but never reaches it. From your perspective, you're constantly accelerating, always feeling the same force pushing you forward. But from the universe's perspective, your velocity increase slows, approaching zero rate of change as you near light speed. This creates a bizarre situation. You could accelerate at 1 million G from your reference frame, feeling crushed under unimaginable force, and still never reach light speed. The universe translates your acceleration into velocity increase according to relativistic equations that guarantee you always fall short. It's like running on a treadmill where the belt speed increases exactly to match your running speed, keeping you forever in place relative to some distant finish line. At the quantum level, this constraint reveals itself in particle physics. In particle accelerators, we slam particles into each other at 99.99% light speed, just a hair's breadth from the ultimate velocity. To add that final 0.001% requires doubling the energy input. To add the next digit requires doubling again. Each successive 9 in the decimal expansion demands exponentially more energy. The Large Hadron Collider, the most powerful particle accelerator ever built, can get protons to 99.99991% light speed. Getting them to 99.9999% would require an accelerator the size of the solar system. Getting to 100% infinite size, infinite energy, impossible. This isn't a technological limitation waiting for better engineering. This is reality saying no. The speed of light isn't a speed limit like the sound barrier, which we can break with sufficient thrust. It's a fundamental boundary of space-time itself, a cosmic wall that gets infinitely harder to push through with each increment closer you approach. The universe has drawn a line, and it enforces that line through the very structure of mass, energy, space, and time. Yet despite all these insurmountable barriers, we can still ask, what if? What if you were somehow traveling at light speed, physics be damned? What would you actually experience? The answer reveals why light speed isn't just unreachable but fundamentally incompatible with existence itself. Chapter 6. Personal experience. If you could somehow reach light speed, your subjective experience would be something utterly incomprehensible, a state so alien it might not qualify as experience at all. Because at light speed, all the relativistic effects we've discussed reach their ultimate conclusion simultaneously, creating a reality that breaks the very concept of consciousness. First, consider time. We've established that time dilation approaches infinity as you approach light speed. At exactly light speed, your clock stops. From your reference frame, zero time elapses during your journey. But what does zero time mean for consciousness? Consciousness requires duration. Thoughts occur over time. Neurons fire in sequence. You process information, form memories, experience the flow of one moment into the next. All of this requires time's passage. At light speed, there is no passage. There's no sequence of moments. Your departure and arrival happen simultaneously from your perspective. You don't experience traveling. You don't experience the journey. You don't experience anything because experience requires temporal duration. And at light speed, duration vanishes. You would exist in what physicists call a null interval, where the space-time distance between events is exactly zero. This creates a profound paradox. The question, what would you experience traveling at light speed, is fundamentally unanswerable because the you that experiences requires time, and at light speed, time doesn't exist. It's like asking what you experience during dreamless sleep, except even dreamless sleep occurs in time. This is timelessness, and timelessness is incompatible with consciousness. From the perspective of a photon, every moment of its existence collapses into a single, eternal now. A photon born in the core of the sun, gradually working its way through the solar interior over hundreds of thousands of years, finally erupting from the surface and racing across space for 8 minutes before striking your eye. Experiences all of this as one instantaneous event. Birth and death in the same moment. No journey in between. For the photon, the sun's core and your retina are the same location in space-time. Now consider space. At light speed, length contraction also reaches infinity. All distances in your direction of travel shrink to exactly zero. The entire universe along your path collapses to a single point. You're simultaneously everywhere and nowhere along your trajectory. The starting point and destination become the same location. The vast gulf of interstellar space vanishes entirely. Combine these effects, zero time, zero distance. What does this mean for the concept of travel itself? Travel implies moving from point A to point B over some duration. At light speed, A and B are the same point and the duration is zero. You don't travel, you simply exist at multiple points in space simultaneously, or perhaps more accurately, you exist at a single point in space-time that encompasses your entire trajectory. This is why massive particles can never reach light speed. It's not just that it requires infinite energy, it's that the very concept of a massive object at light speed is meaningless. Massive objects have rest frames, reference frames in which they're stationary. Light has no rest frame. There's no reference frame in which a photon is at rest. Light exists only in motion, not through space and time, but as a fundamental vibration of the electromagnetic field, propagating at the maximum speed space-time allows. If you somehow became light-like, you'd lose your rest frame. There would be no perspective from which you're standing still, no viewpoint from which you can observe the universe passing by. You'd cease to be an object in space and become a process of propagation, something more verb than noun. You wouldn't travel through space-time. You'd become a path through space-time, a world line connecting events with no internal temporal extent. What about perception? We've seen how the universe visually distorts at relativistic speeds. At light speed, this distortion reaches its ultimate form. All light from the universe ahead of you, from the sides, from behind you, blue shifts and aberrates into a single, infinitely bright, infinitely small point directly ahead. But ahead loses meaning when all distances collapse to zero. That point is simultaneously everywhere in your field of view because your field of view encompasses the entire universe compressed to zero extent. The Doppler shift becomes infinite. The cosmic microwave background, those faint radio photons permeating space at 2.7 Kelvin, blue shifts to infinite energy. every photon in the universe blue shifts to infinite energy from your perspective. The entire electromagnetic spectrum compresses into a single frequency, infinity. This is physically meaningless. It's another way the universe signals that light speed is forbidden territory for observers. In 2012, physicist John Baez at the University of California analyzed what he called the photon's eye view of the universe. He concluded that the concept is mathematically undefined. There simply is no consistent way to construct a reference frame moving at light speed. The Lorentz transformation equations, which convert between different reference frames, involve dividing by zero at light speed. The mathematics breaks down. It's not that we don't know what things look like at light speed. It's that the question itself is malformed, asking about a perspective that cannot exist within the structure of special relativity. Consider what this means for information processing. Your brain operates through electrochemical signals, neurons firing in complex patterns over time. These signals propagate at roughly 100 meters per second along your neurons, vastly slower than light speed. For you to think, information must move through your neural networks, and this movement requires time. At light speed, with your clock stopped, no time passes, no signals propagate, no thoughts form. Your consciousness would be frozen in a single, instantaneous state with no duration, no change, no content. You might argue, but from my perspective, time passes normally. I'd experience the journey at my own clock rate. And this is true at 99% light speed, 99.9%, even 99.999%. But at exactly light speed, your clock doesn't tick slowly, it stops entirely. There is no normal passage of time from your perspective, because there is no passage of time at all. The distinction between moving slowly and not moving at all is absolute. This reveals something profound about the nature of consciousness and observation in relativity. Observation requires an observer with a valid reference frame, a perspective from which space-time can be divided into space and time, where causality operates, where events unfold in sequence. At light speed, no such reference frame exists. You cannot be an observer at light speed because observation itself requires time, and light speed is the boundary where time ceases. Think about the implications for communication. If you were traveling at light speed and trying to send a signal back home, that signal would also travel at light speed. From your perspective at light speed, with zero time passing, you'd transmit and receive the signal instantaneously. But instantaneous, in a reference frame with zero duration, is meaningless. There's no before signal and after signal. States because there's no before and after. This is why relativity treats light fundamentally differently from massive particles. Massive particles have world lines through space-time, continuous paths connecting their past to their future. Light has null world lines, paths along which the space-time interval is exactly zero. These null world lines form the boundary between past and future in space-time diagrams, the light cones that define causality. Light doesn't travel through space-time the way particles do. Light defines the structure of space-time itself. If you could somehow reach light speed, you wouldn't become faster, you'd become something else entirely. You'd transform from an object that persists through time into something closer to a geometric feature of space-time itself. You join the electromagnetic field, becoming a pattern of oscillation rather than a thing that oscillates. Your identity as a distinct entity would dissolve into the fundamental fabric of reality. The closest analogy might be this. Imagine you're watching a movie, experiencing the story frame by frame as time progresses. Traveling near light speed is like fast-forwarding through the movie, experiencing more story frames in less of your personal time. But reaching light speed isn't like forwarding the movie infinitely fast. It's like ceasing to be a viewer and becoming one of the still photographs that makes up a single frame. You don't experience the movie faster, you stop experiencing the movie entirely and become part of the medium itself. This is the ultimate impossibility of light-speed travel. It's not just practically impossible, requiring infinite energy and acceleration. It's conceptually impossible, requiring the existence of an observer without time, perception without duration, consciousness without sequence. You cannot experience light-speed travel because you and experience and travel are all concepts that require time. And at light speed, time is not slow or fast. It simply isn't. Yet this impossible boundary teaches us something remarkable about reality. The speed of light isn't arbitrary. It's the speed at which the universe operates, the rate at which cause and effect propagate, the maximum velocity of information transfer. And this speed limit creates a structure in space-time that makes the universe comprehensible, causal, and navigable. Without it, simultaneity would be absolute and paradoxes would proliferate. The light speed limit isn't a constraint on what's possible. It's the foundation that makes anything possible at all. Chapter 7, Causality Breakdown. The speed of light doesn't just limit how fast you can travel. It protects the fundamental structure of cause and effect in the universe. If you could exceed light speed even for an instant, you could violate causality itself, sending signals backward in time and creating paradoxes that would unravel the logical consistency of reality. This seems like an exaggeration, but the mathematics are unambiguous. Special relativity reveals that the order of events in space-time is not absolute. Two events that appear simultaneous in one reference frame occur at different times in another reference frame, moving relative to the first. This relativity of simultaneity is harmless as long as signals travel at or below light speed. But the moment you exceed light speed, you can construct scenarios where effects precede causes. Here's how it works. Imagine you're on Earth and your friend is on Mars, 12 light minutes away. You send a faster-than-light message to Mars, arriving instantly from your reference frame. Your friend receives it and immediately sends a faster-than-light reply back. From your mutual rest frame, the round trip is instantaneous, no problem. But now introduce a spacecraft traveling at 80% light speed relative to both Earth and Mars. From the spacecraft's reference frame, due to relativity of simultaneity, the order of events is different. In the spacecraft's frame, your friend's reply might be sent before your original message, according to the spacecraft's simultaneity definition. If both you and your friend use this spacecraft's reference frame for your faster-than-light communication, the reply could arrive on Earth before you sent the original message. Effect precedes cause. You've created a causal loop. In 1962, physicists A.E. Everett and Roman Weisskopf at Harvard analyzed this scenario in detail. They proved that any form of faster-than-light communication, regardless of mechanism, inevitably allows for closed, time-like curves, loops in space-time where you can interact with your own past. These loops create logical paradoxes. You could send a message to yourself in the past telling yourself not to send that message, creating a contradiction with no resolution. The universe appears to prevent these paradoxes by enforcing the light speed limit absolutely, not as a speed limit in the conventional sense, but as a causal boundary. Light speed is the maximum rate at which cause can propagate to effect. Any signal traveling faster would be a signal that can propagate backward in time in some reference frame, and the universe doesn't permit this. This is why physics treats light speed as fundamental in ways that go beyond simple velocity. In Einstein's equations, light speed appears not as a speed, but as a conversion factor between space and time, the rate at which space-like separation converts to time-like separation in space-time. It's denoted c, and it appears everywhere. In E to mc2 in the Lorentz transformations, in Maxwell's equations. It's woven into the fabric of reality at the deepest level. Consider what would happen if light speed were different. If light traveled slower, say 100 kilometers per second instead of 300,000, the relativistic effects would kick in at much lower velocities. A car on the highway would experience measurable time dilation. GPS satellites would require major corrections. The chemistry of atoms would be different because electrons orbit at velocities where relativistic effects become significant. The universe would be fundamentally different. If light speed were infinite, as Newton and classical physics assumed, then simultaneity would be absolute. There would be a universal present moment throughout the entire universe. Cause and effect would operate instantaneously across any distance. This sounds convenient, but it creates problems. Electromagnetic waves wouldn't exist in the form we know them. Maxwell's equations, which describe electricity and magnetism, inherently predict that electromagnetic disturbances propagate at finite speed, c. With infinite light speed, electromagnetism as we understand it wouldn't function. The finite speed of light also creates a cosmological structure. It limits how much of the universe we can observe. Light from distant galaxies takes time to reach us, so we see those galaxies as they were in the past. The observable universe has a boundary, a cosmic horizon approximately 46 billion light-years away, beyond which light hasn't had time to reach us since the Big Bang. If light speed were infinite, we'd see the entire universe instantaneously, potentially infinite in extent, overwhelmingly chaotic. In 2015, cosmologist Lawrence Krauss at Arizona State University argued that the finite speed of light is essential for life. It creates temporal buffers between events, allowing complex systems to evolve without instantaneous disruption from distant cosmic events. It establishes local causality, where events in your immediate vicinity determine your experience more than distant events. Without this light speed limit, cause and effect would be immediate and universal, making stable structures like stars, planets, and living organisms far more difficult to form and maintain. The speed limit also protects energy conservation. If you could accelerate an object beyond light speed, the mathematics of relativity predict your kinetic energy would become imaginary, a meaningless mathematical value. This isn't just a weird equation. It's the universe saying that the concept of faster-than-light massive objects is physically meaningless, incompatible with the conservation laws that govern energy and momentum. Some physicists have speculated about hypothetical particles called tachyons that always travel faster than light, never slower. These particles would have imaginary mass and bizarre properties. They lose energy as they accelerate and gain energy as they slow down. If tachyons exist, they'd create vacuum instabilities, spontaneously generating from nothing and violating energy conservation. Most physicists consider tachyons mathematical curiosities rather than physical possibilities, artifacts of equations rather than real entities. Other proposals for circumventing the light speed limit involve warping space-time itself rather than moving through it. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, suggests contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that moves faster than light while the spacecraft inside remains stationary relative to local space. This doesn't violate relativity because the spacecraft itself never exceeds light speed through local space-time. But the Alcubierre drive requires exotic matter with negative energy density, something never observed and possibly forbidden by quantum field theory. Even if exotic matter exists, the energy requirements are staggering, estimated at the mass energy equivalent of Jupiter or more. And theoretical analyses suggest that causality violations might still occur. An Alcubierre drive could potentially be used to construct closed time-like curves, bringing us back to the same paradoxes. Wormholes, hypothetical tunnels, through space-time connecting distant regions, face similar problems. General relativity allows wormhole solutions mathematically, but keeping a wormhole open requires exotic matter, and traversable wormholes might allow time travel by creating paths through space-time that loop back to the past. The universe might prevent this through quantum effects, Stephen Hawking's chronology protection conjecture suggests that quantum fluctuations become infinite at the mouth of any time machine, preventing its formation. All roads lead back to the same conclusion. The universe is structured to prevent causality violations, and the mechanism for this protection is the light speed limit. It's not that we haven't figured out how to exceed light speed, it's that exceeding light speed would break the logical consistency of the universe, and nature doesn't permit that. Think about what this means philosophically. The universe has rules, and these rules are not arbitrary. They form a coherent, logical structure where cause precedes effect, where information cannot travel from future to past, where contradictions cannot exist. The speed of light is one expression of this deeper principle. It's a cosmic enforcement mechanism ensuring that reality makes sense. This is why modern physics treats the speed of light as definitional. Since 1983, the meter has been defined as the distance light travels in 1,299,792,004 of a second. We don't measure the speed of light anymore. We use the speed of light to define our units of measurement. It's that fundamental. When you understand causality protection, the impossibility of light speed travel for massive objects becomes less frustrating and more profound. You're not being denied access to high velocities because the universe is stingy. You're being protected from logical inconsistency, from a reality where effects could precede causes, where you could alter your own past, where the narrative structure of existence would collapse. The light speed limit is the universe's way of maintaining its own coherence. It's a boundary not between fast and faster, but between causality and chaos, between a comprehensible cosmos and logical paradox. You cannot reach light speed because doing so would mean stepping outside the causal structure that makes you a meaningful concept persisting through time. Yet even knowing all this, we can still wonder, are there edge cases? Scenarios where light speed might be approached or even exceeded without violating the fundamental principles. The answer reveals just how carefully the universe has constructed its prohibitions. Chapter 8. Edge cases. The universe enforces the light speed limit with remarkable precision, but nature contains phenomena that seem to challenge or circumvent this boundary. These edge cases reveal just how subtle and absolute the cosmic speed limit truly is, because in every apparent violation, the universe finds a way to preserve causality and relativity. Consider the expansion of space itself. Distant galaxies are receding from us at velocities exceeding light speed due to the expansion of the universe. A galaxy currently 14 billion light-years away is moving away from us at roughly 3.2 times light speed. A galaxy at the cosmic horizon, 46 billion light-years distant, recedes at nearly 3 times light speed. These aren't theoretical predictions. We observe this through redshift measurements. How does this not violate relativity? The answer lies in what's actually moving. The galaxies aren't moving through space at superluminal speeds. Space itself is expanding between us and them. Think of dots on a balloon surface as you inflate the balloon. The dots move apart not because they're sliding across the rubber, but because the rubber itself is stretching. No individual dot moves faster than light relative to its local patch of rubber, yet distant dots can separate faster than light due to the accumulated expansion. This distinction is crucial. Special relativity limits how fast objects can move through space-time, but it places no limit on how fast space-time itself can expand. The galaxies have low velocities relative to their local space, well below light speed. It's the space between us and them that's growing, carrying them along for the ride. No information travels faster than light, no causality is violated, and relativity remains intact. But this creates an eerie consequence. Galaxies beyond the cosmic horizon are receding so fast that light they emit today will never reach us, no matter how long we wait. They've passed beyond a boundary called the Hubble sphere, where recession velocity equals light speed. We can still see galaxies beyond this boundary because we're seeing light they emitted billions of years ago when they were closer. But light emitted by these galaxies today is trapped, fighting against the expanding space, never to complete its journey to Earth. These galaxies have effectively exited our observable universe, not by moving, but by having space grow between us faster than light can traverse it. Another apparent exception appears in quantum mechanics. Quantum entanglement creates correlations between particles that persist instantaneously across any distance. Measure the spin of one entangled electron, and you instantly know the spin of its partner, even if that partner is on the other side of the galaxy. Einstein called this spooky action at a distance and thought it might violate relativity by allowing faster-than-light communication. But experiments since the 1980s, particularly those by Alain Aspect at the University of Paris, have confirmed that entanglement, while real, cannot transmit information faster than light. The measurement results at each location appear random. Only when you compare the results using conventional light-speed limited communication do the correlations become apparent. The universe has carefully structured quantum mechanics so that entanglement provides correlation without causation, maintaining the light speed limit for information transfer. In 2022, the Nobel Prize in Physics was awarded for experimental verification that quantum mechanics truly exhibits this non-locality while still respecting relativity. The correlations are genuine and instantaneous, but they're not signals. They don't carry information from one particle to the other. They're pre-existing correlations in the quantum state, revealed but not created by measurement. Causality remains protected. Quantum tunneling presents another interesting edge case. Particles occasionally pass through energy barriers they classically shouldn't be able to cross, appearing on the other side, seemingly instantaneously. In 1982, physicist Günther Niemitz at the University of Cologne claimed to measure Mozart's 40th Symphony tunneling through a barrier faster than light, arriving before an identical signal transmitted through air over the same distance. But detailed analysis revealed that what tunneled wasn't the information in the music, but the wave packet's peak. The actual information content of the signal, encoded in the wave's modulation, never exceeded light speed. It's like watching a wave crest move along a rope faster than the individual fibers. The pattern moves quickly, but no individual piece of the rope travels at that speed. Quantum tunneling respects the light speed limit for information, even while allowing apparent superluminal motion of wave features. Perhaps the most dramatic apparent exception occurs with Cherenkov radiation. When charged particles travel through a medium like water faster than light travels in that medium, they emit a characteristic blue glow. Nuclear reactors produce this eerie blue light from electrons moving at 75% of light speed in vacuum, which exceeds the speed of light in water, about 75% of vacuum light speed. The particles are supersonic, relative to electromagnetic waves in the medium, creating a light speed equivalent of a sonic boom. But this isn't a violation of relativity. The universal speed limit is the speed of light in vacuum, approximately 299,792 kilometers per second. Light slows down in materials due to interactions with atoms, but this is still electromagnetic radiation obeying relativity. The charged particle is moving faster than light can travel in water, but still well below the cosmic speed limit. It's like a swimmer moving faster than waves travel in a pool, without exceeding the speed of sound in air. No causality violation occurs. Another fascinating case involves the phase velocity of waves. Under certain conditions, the phase velocity, the speed at which wave crests move, can exceed light speed. In anomalous dispersion, where a material's refractive index varies strongly with frequency, experiments have measured phase velocities hundreds of times faster than light. In 2000, physicists Lijun Wang and colleagues at the NEC Research Institute sent a light pulse through a specially prepared chamber of cesium gas. The peak of the pulse exited the chamber before it finished entering, appearing to travel at 310 times light speed. Media reports proclaimed faster-than-light travel, but the reality was subtler. The pulse peak moved faster than light, but the actual information, encoded in the pulse shape's changes, traveled at or below light speed. Once again, the universe protected causality while allowing exotic wave behavior. Even the structure of space-time admits solutions that seem to permit faster-than-light travel. In general relativity, space-time can be curved and distorted. Rotating black holes, described by the Kerr metric, contain regions where space-time is dragged around the black hole at speeds exceeding light speed. But these aren't material objects moving faster than light. It's space-time itself rotating, carrying everything along with it, similar to how space-time expansion carries galaxies. More exotic solutions exist. The Gödel metric, discovered by mathematician Kurt Gödel in 1949, describes a rotating universe where closed time-like curves exist, allowing time travel without any apparent paradox. Travel far enough in space in a Gödel universe and you arrive back at your starting point in space-time earlier than when you left. This would allow you to visit your own past, but our universe isn't a Gödel universe. Observations show our cosmos is expanding, not rotating in the required way. The solution is mathematically valid, but physically irrelevant. The universe we inhabit has carefully avoided these geometries that would permit causality violations. Once again, nature chooses options that preserve the logical consistency of cause and effect. All these edge cases share a common theme. The universe permits exotic behavior at the boundaries of physics, but always in ways that preserve the fundamental light speed limit for information and causality. Space can expand faster than light because no information travels with the expansion. Quantum correlations can be instantaneous because they don't transmit information. Wave features can exceed light speed because they're not carrying information. Space-time can rotate superluminally because it's geometry, not matter. The pattern is clear. Every time we discover a phenomenon that seems to violate the light speed limit, closer examination reveals the violation is apparent, not real. The universe has structured itself with remarkable consistency to prevent causality violations while still allowing rich and surprising behavior. The light speed limit isn't a simple fence you might find a gate through. It's a fundamental property woven into every aspect of physical law. This universality suggests something profound. The speed of light isn't just a property of light. It's a property of reality itself, of the relationship between space and time, of the structure of causality. Light moves at this speed not because photons are special, but because this is the maximum speed at which any causal influence can propagate through the fabric of space-time. Light happens to move at this speed because photons are massless and thus must travel at the maximum possible velocity. Understanding these edge cases makes the impossibility of light speed travel more comprehensible. You're not fighting against a simple speed restriction. You're confronting the fundamental architecture of the universe, a structure that has been carefully constructed to maintain logical consistency across all possible scenarios. Every loophole closes. Every potential exception resolves into confirmation of the rule. The cosmos protects its boundaries with remarkable thoroughness.
Chapter 9. Time's arrow. The light speed limit creates something even more profound than a maximum velocity. It structures time itself, giving temporal experience a direction, a flow from past to future that defines your existence. Understanding how light speed relates to time's arrow reveals why you perceive reality as a sequence of moments rather than a static four-dimensional block. In space-time, physics treats time as a dimension similar to space. Your existence traces out a world line, a continuous path through four-dimensional space-time, connecting your past to your future. Every moment of your life is a point on this world line, and the complete line represents your entire existence from birth to death, laid out like a thread through space-time. But here's what's strange. The equations of physics are mostly time-symmetric. If you filmed most physical processes and played the video backward, the reverse process would obey the same physical laws. An electron orbiting a proton works the same forward or backward in time. Planets orbiting stars, billiard balls colliding. Light waves propagating most fundamental physics doesn't distinguish between past and future, yet you experience time flowing in only one direction. You remember the past, but not the future. You can influence the future, but not the past. Eggs break, but don't unbreak. Coffee cools but doesn't spontaneously heat. Entropy increases. The universe has a clear temporal direction, an arrow of time pointing from past to future. The light speed limit is intimately connected to this arrow. In space-time diagrams, physicists draw light cones, geometric structures representing all possible paths light could take from a given event. The future light cone contains all events that could be causally influenced by the present event. The past light cone contains all events that could have causally influenced it. These cones divide space-time into regions: events you can affect, events that can affect you, and events that can do neither. The boundary of these cones moves outward at light speed. This is why light speed defines causality. An event can only influence another event if a signal traveling at or below light speed can connect them. The light speed limit transforms causality from an abstract concept into a geometric feature of space-time. Your future is literally the region of space-time inside your future light cone, and your past is the region inside your past light cone. This creates a structure in space-time that wouldn't exist if light speed were infinite. With infinite light speed, your light cone would encompass the entire universe instantaneously. Every event would be causally connected to every other event simultaneously. Past and future would lose their distinction because causal influence would be instantaneous. The temporal structure of the universe would collapse. But with finite light speed, the universe has temporal depth. Events separate into past, present, and future based on causal relationships. You can draw a clear line from causes to effects because causes must precede effects by enough time for a light speed signal to connect them. This creates the arrow of time at a fundamental level. In 1927, physicist Arthur Eddington coined the term arrow of time to describe this temporal asymmetry. He identified several different arrows. The thermodynamic arrow entropy increases, the cosmological arrow the universe expands. The psychological arrow we remember the past, not the future, and the causal arrow causes precede effects. These arrows all align, pointing in the same temporal direction, and the light speed limit helps enforce this alignment. Consider what happens when you observe a distant star. The light reaching your eye left that star years ago, carrying information about the star's past state. The light speed delay creates a direct connection between observed events and past events. You literally see the past when you look at distant objects. The Andromeda Galaxy appears as it was 2.5 million years ago. The most distant galaxies we observe appear as they were over 13 billion years ago, when the universe was young. This light speed delay creates a cosmic history book. The farther you look into space, the farther you look back in time. The universe provides its own fossil record, visible in the sky, with light speed as the limiting factor determining how far back we can see. Without this finite light speed, without this delay between event and observation, the universe would have no observable history. Everything would be simultaneous. The speed of light also determines the rate at which information propagates. Information cannot travel faster than light, which means the universe has a maximum rate of information transfer, 1 bit per Planck length per Planck time, an unfathomably large but finite limit. This creates a fundamental grain to the universe's information processing, a maximum bandwidth for reality itself. In 2002, physicist Seth Lloyd at MIT calculated that the observable universe has processed approximately 10,120 bits of information since the Big Bang. That's a vast number, but it's finite, constrained by the light speed limit on information propagation. If information could travel infinitely fast, the universe could process infinite information in finite time, leading to paradoxes and singularities in the mathematical description of physical processes. The light speed limit also creates what physicists call horizons, boundaries beyond which information cannot reach you. We've discussed the cosmic horizon, beyond which galaxies recede faster than light due to cosmic expansion, but there are other horizons. Near a black hole, there's an event horizon, a boundary where escape velocity equals light speed. Nothing inside, not even light itself, can escape because doing so would require exceeding light speed. The event horizon is a direct consequence of the light speed limit combining with gravity. These horizons create a profound feature of the universe. Locality events beyond your horizon cannot affect you. You're causally isolated from them until light has time to cross the intervening distance. This creates a bubble of local causality around every observer, a region within which causes and effects can interact, surrounded by a boundary beyond which events are causally disconnected. Locality is essential for making sense of the universe. It means you can understand physics in your region of space without needing to know the state of the entire cosmos simultaneously. You can perform experiments, make predictions, and understand causes without accounting for distant galaxies on the other side of the observable universe. The finite light speed creates this local structure, making physics comprehensible and deterministic within causal boundaries. Without light speed limits, without horizons, everything would affect everything else instantaneously. The butterfly effect would be literal and immediate. A butterfly flapping its wings on Earth would instantly influence events in distant galaxies. Physics would be intractable, requiring simultaneous solution of equations encompassing the entire universe to predict any local event. The universe would be too interconnected to comprehend. Time's arrow also manifests in thermodynamics. Entropy, a measure of disorder, increases over time in closed systems. This creates temporal asymmetry. Processes naturally flow from order to disorder, from low entropy to high entropy. A broken egg has higher entropy than an intact egg, and entropy increase explains why eggs break but don't spontaneously reassemble. But why does entropy increase? The answer connects to the Big Bang and the special low-entropy initial state of the universe. The early universe was remarkably ordered, with matter and energy distributed smoothly and uniformly. As the universe evolved, gravity created structure. Stars, galaxies, planets. This increased local order, but at the cost of increased total entropy. The arrow of time points from the ordered past toward the disordered future. The light speed limit constrains how fast entropy can spread. Disorder propagates at or below light speed. A glass shattering on the floor creates a localized entropy increase that propagates outward as sound waves, heat, and scattered fragments, all traveling at or below light speed. If entropy could increase instantaneously everywhere, the thermodynamic arrow would have no spatial structure. Instead, it spreads in an outward wave from each local event, creating a temporal flow that aligns with causal structure. In 2014, physicist Sean Carroll at Caltech argued that time's arrow ultimately derives from the boundary conditions of the universe, particularly the low-entropy Big Bang. But the light speed limit shapes how this arrow manifests in our experience. It creates the causal structure, the information delays, the horizons that give time its distinctive forward flow in our perception. Think about memory. You remember the past because your brain stores information about past events in physical structures, patterns of neurons and synapses. This storage process increases entropy. The energy required to encode memories generates heat, increasing disorder. Memory works forward in time because entropy increases forward in time, and entropy increases forward in time because of the universe's special initial conditions, combined with the causal structure enforced by light speed limits. You cannot remember the future, not because future events don't exist in the four-dimensional space-time block, but because causal influence flows from past to future, and information encoding requires causal interaction. The future cannot send information to the past without violating light speed limits. So memory only works in one temporal direction. This creates a poignant realization. Your subjective experience of time flowing, of moments passing one after another, of the present moment advancing from past toward future, is intimately tied to the light speed limit. Without this cosmic speed limit, without the causal structure it creates, time might not have the distinctive flow you experience. Past, present, and future might blur into a timeless whole, incomprehensible to consciousness that evolved in a universe where causes precede effects. The impossibility of reaching light speed is thus connected to the impossibility of reversing time, of stepping outside causality, of experiencing existence in any way fundamentally different from the temporal flow you know. Light speed is the boundary between time and timelessness, between causal structure and chaos, between a universe that makes sense and one that cannot support conscious observers.
Chapter 10: Ultimate Boundaries. We've explored what would happen if you traveled at light speed, and at every turn we've encountered the same answer: impossibility. Not the impossibility of lacking sufficient technology, but the impossibility of logical contradiction, of mathematical breakdown, of reality saying this boundary shall not be crossed. And this reveals something profound about the nature of physical law. The universe is not arbitrary. It operates according to principles that form a coherent, consistent logical structure. The speed of light isn't just one speed among many. It's a fundamental constant woven into the fabric of space-time itself, appearing in equations that describe electricity, magnetism, gravity, and quantum mechanics. It's denoted c in physics, and it emerges from the deepest symmetries of nature. In 1905, Einstein derived special relativity not from studying light, but from analyzing the symmetries of physical laws. He asked, what transformations leave the laws of physics unchanged? The answer is Lorentz transformations, mathematical operations that mix space and time coordinates. These transformations have a special invariant speed built into them, a velocity that's the same in all reference frames. This invariant speed happens to be the speed of light, but it's more fundamentally the maximum speed of causality itself. Light travels at this speed not because photons are special, but because photons are massless and therefore must travel at the maximum possible velocity. If we lived in a universe without light but with the same space-time structure, the speed limit would still exist. We might call it the maximum causal speed or the invariant velocity. We call it the speed of light only because light happens to move at it. This reveals a deep truth. The universe has boundaries, and these boundaries are not restrictions but foundations. They're not limits on what can happen, but structural principles that make things happen in comprehensible ways. The light speed limit creates causality, distinguishes past from future, allows for locality, makes physics solvable, and permits conscious observers to exist. Consider what physics looks like at the boundaries. We've focused on the light speed limit, but the universe has other fundamental boundaries. The Planck length, approximately 1.6 x 10 to 35 meters, is thought to be the smallest meaningful distance in quantum gravity. Below this scale, space-time itself might become grainy or quantum foam-like, and the very concept of distance might break down. The Planck time, about 5.4 x 10 to 44 seconds, is the shortest meaningful duration, the time it takes light to cross a Planck length. The Planck energy, roughly 1019 billion electron volts, is the energy scale where quantum effects and gravitational effects become equally important. These Planck scales represent boundaries where our current theories reach their limits. Just as you cannot accelerate to light speed without confronting infinite energy requirements, you cannot probe beyond Planck scales without confronting the quantum nature of space-time itself. The universe establishes boundaries at multiple scales, each protecting the logical consistency of physical law in its domain. In 2004, physicist Juan Maldacena at the Institute for Advanced Study proposed a profound connection between gravity and quantum mechanics through what's called holographic duality. This suggests that all the information in a volume of space can be encoded on its boundary, and that the light speed limit plays a crucial role in establishing this correspondence. The universe might be fundamentally holographic, with three-dimensional reality emerging from information encoded on two-dimensional surfaces, and light speed determining how information propagates between bulk and boundary. These deep connections suggest that the speed of light is not an isolated fact, but part of a unified structure. The same principles that establish light speed limits also determine Planck scales, connect quantum mechanics to gravity, and govern the holographic nature of space-time. We're glimpsing a unified foundation where all physical laws emerge from common symmetries and principles. What does this mean for the possibility of faster-than-light travel? It means you're not just confronting one limitation, but an entire interconnected structure. To exceed light speed, you'd need to fundamentally rewrite the laws of physics, not just in one area, but across the board. You'd need to change how space and time relate, how causality operates, how information propagates, how quantum mechanics functions, potentially even how gravity works. Some physicists speculate about modifications to relativity that might permit superluminal travel. Theories with extra dimensions, modified dispersion relations, or quantum gravity effects have been explored. But every proposal either requires exotic conditions we've never observed or creates new paradoxes requiring resolution. The universe seems remarkably resistant to modifications that would permit causality violation. This resistance suggests that the light speed limit might be what physicists call a no-go theorem, a proven impossibility like creating energy from nothing or cooling systems below absolute zero. These aren't engineering challenges awaiting better technology. They're mathematical theorems demonstrating logical impossibility. The light speed limit for massive objects might be in this category, not just currently impossible, but impossible in principle. Yet the universe continues to surprise us. Quantum mechanics revealed phenomena Newton never imagined. General relativity showed that space and time are dynamic and curved. Dark energy demonstrates that cosmic expansion can accelerate. We've been wrong before about what's possible. Might we be wrong about light speed? The difference is that previous revolutionary discoveries revealed new phenomena while maintaining consistency with established principles. Quantum mechanics didn't violate conservation of energy, it revealed new forms of energy and uncertainty. Relativity didn't eliminate causality, it refined our understanding of space and time while strengthening causal structure. Dark energy doesn't break thermodynamics. It represents a form of energy density in vacuum. A discovery that allowed faster-than-light travel would be different. It wouldn't just add new physics, it would require dismantling the causal structure we've confirmed through countless experiments. It would need to resolve the paradoxes of time travel, explain how information can travel faster than causality permits, and reconcile with every observation confirming special relativity. The burden of proof is extraordinary because the claim contradicts not one theory, but the entire edifice of modern physics. This doesn't mean we should stop exploring boundaries. Science progresses by probing limits, testing assumptions, and discovering exceptions, but it means we should recognize that the light speed limit is extraordinarily well established, confirmed by every high-energy experiment, every astronomical observation, every GPS satellite, every particle accelerator. Overturning it would require evidence as extraordinary as the claim. Perhaps the question itself is wrong. Instead of asking how can we exceed light speed, maybe we should ask what can we accomplish within light speed constraints. The universe has given us a vast playground. We can explore our solar system. We could potentially reach nearby stars within human lifetimes from the traveler's perspective using relativistic time dilation. We can observe the entire cosmos through telescopes, seeing billions of light years in every direction. The light speed limit doesn't imprison us in our local region. It structures the universe in ways that make it comprehensible, navigable, and meaningful. It creates horizons that establish locality, time delays that provide cosmic history, causal boundaries that protect consistency. Rather than a cage, it's a framework within which reality can operate coherently. Think about what's possible within this framework. A spacecraft traveling at 99.999999% light speed could reach the Andromeda Galaxy, 2.5 million light-years away, in about 35 years of ship time due to time dilation. The crew would age 35 years while 2.5 million years pass on Earth. But from their perspective, they've crossed intergalactic space within a human lifetime. The light speed limit doesn't prevent this journey, it makes it possible through time dilation. In principle, with sufficient energy and shielding, you could traverse the entire observable universe within a human lifetime of ship time. You'd return to find eons have passed, civilizations risen and fallen, stars burned out, but you would have journeyed across cosmic distances. The light speed limit creates this asymmetry between coordinate time and proper time, allowing relativistic travelers to be time travelers into the future. Perhaps this is the ultimate lesson. The boundaries of physics aren't walls keeping you trapped. They're the structural principles that make existence possible, comprehensible, and navigable. The speed of light doesn't limit what you can experience. It defines how experience relates to reality. It doesn't prevent exploration. It establishes the rules by which exploration occurs. You cannot reach light speed because you are a being who exists in time, who experiences causality, who forms memories of the past and acts toward the future. These aspects of your existence require the temporal structure that light speed creates. To reach light speed would mean leaving time, abandoning causality, dissolving the very concept of self that experiences anything at all. The impossibility isn't a frustration, it's a foundation. It's the universe saying these are the rules that make reality real, that make consciousness possible, that allow causes to lead to effects in comprehensible ways. These boundaries aren't limitations on what the universe can do. They're the scaffolding that holds everything together. And in recognizing these boundaries, in understanding why they exist and what they protect, you gain something more valuable than unlimited speed. You gain insight into the deep structure of reality itself, into the principles that govern existence, into the profound logic underlying the cosmos. You see that the universe is not arbitrary chaos, but elegant order, not random constraints, but necessary foundations. The light speed limit is one expression of this order. It's the universe's way of maintaining its own consistency, of protecting causality, of allowing complex structures like stars and planets and living organisms and conscious minds to exist and persist. Now, it's not keeping you from something, it's making you possible. Throughout this journey, we've discovered that traveling at light speed isn't just practically impossible, it's conceptually impossible. We've seen how your mass would approach infinity, requiring infinite energy to accelerate further. We've explored how time would stop completely from your perspective, eliminating the duration necessary for consciousness. We've witnessed space compressing to zero distance, collapsing the entire universe into a single point along your trajectory. We've experienced the visual nightmare of light, shifting to invisible, deadly frequencies, with the cosmos ahead becoming a lethal flood of gamma rays, while the universe behind fades into red-shifted darkness. We've confronted the biological impossibility of accelerating to these speeds, where even with unlimited energy, the asymptotic mathematics guarantee you'll never reach the ultimate threshold. We've examined what it means that experience itself requires time, and at light speed, time ceases to exist. But perhaps the most profound insight is this: the speed of light isn't arbitrary. It's not a cosmic speed limit chosen randomly from infinite possibilities. It's a fundamental property of space-time itself, a conversion factor between space and time, the maximum speed at which causality can propagate. It emerges from the deep symmetries of nature, appearing in every fundamental equation, from electromagnetism to relativity to quantum field theory. This speed limit protects causality, preventing effects from preceding causes. It creates temporal structure, giving the universe a meaningful distinction between past and future. It establishes locality, allowing regions of space to evolve semi-independently rather than being instantly influenced by every distant event. It makes the cosmos comprehensible rather than chaotic, navigable rather than paradoxical. The universe has boundaries, and these boundaries are not restrictions but foundations. They're not limitations on what can happen, but structural principles that make things happen in comprehensible ways. Without the light speed limit, causality would break down. Time travel paradoxes would proliferate. the logical consistency of reality would collapse. As you go about your day after watching this, remember that the light speed limit is actively shaping your experience right now. When you see the sun, you're seeing it as it was 8 minutes ago, the time light takes to cross 150 million kilometers. When you look at the night sky, you're seeing cosmic history, Betelgeuse as it was 700 years ago, Andromeda as it was 2.5 million years ago, the most distant visible quasar as it was over 13 billion years ago when the universe was young. The finite speed of light means you're always seeing the past when you look at anything beyond arm's reach. Even in conversation, when someone speaks to you from across a room, you're hearing them as they were milliseconds ago, the time sound takes to cross that distance. Reality is not instantaneous. It unfolds at the speed of causality, at the maximum rate information can propagate, at the invariant speed we call light speed. Consider the GPS satellite orbiting overhead, its onboard atomic clock ticking at a slightly different rate than yours due to relativistic effects. The engineers who designed GPS had to account for both special relativistic time dilation from the satellite's velocity and general relativistic time dilation from Earth's gravity. If they hadn't incorporated Einstein's insights about the relativity of time, your navigation would drift kilometers off course within hours. The entire global positioning system exists as a testament to the reality of relativistic effects. Think about the particle accelerators probing nature's deepest secrets, accelerating protons to 99.99% light speed, and watching their mass increase exactly as Einstein predicted. Consider the muons created in Earth's upper atmosphere, particles that should decay long before reaching the ground, yet regularly do so because time dilation extends their lifespan from their reference frame. Every high-energy experiment, every astronomical observation, every precision measurement confirms the same fundamental truth. Space-time has a structure, and that structure includes an invariant maximum speed. You are not separate from this structure. You are woven into it. Your existence unfolds in time. Your consciousness experiences moments in sequence. Your memories preserve information about the past, and your actions influence the future, all because the universe has a causal structure enforced by the light speed limit. Without this limit, without this boundary between possible and impossible, you couldn't exist as a temporal being who experiences, remembers, and chooses. The impossibility of light speed travel is thus intimately connected to the possibility of your existence. You cannot reach light speed because doing so would mean leaving the temporal dimension, abandoning causality, dissolving the very structure that makes you a meaningful concept. The boundary isn't keeping you from something, it's making you possible. In exploring this impossibility, we've glimpsed the deep logic of the cosmos. We've seen that the universe is not arbitrary but elegantly structured, not randomly constrained, but necessarily consistent. The light speed limit is one manifestation of this consistency, one expression of the fundamental principles that make reality comprehensible, causal, and capable of supporting conscious observers who can wonder about its nature. Perhaps that's the ultimate revelation. The boundaries of physics aren't frustrations to overcome, but insights into reality's foundation. Every impossibility teaches us something profound about how the universe works. The impossibility of perpetual motion machines revealed energy conservation. The impossibility of absolute zero revealed quantum mechanics. And the impossibility of light-speed travel reveals the structure of space-time itself, the nature of causality, and the deep connection between physical limits and logical consistency. You cannot travel at light speed, and now you understand why. Not because the universe is cruel or limiting, but because the universe is logical, consistent, and structured in ways that make existence possible. The light speed limit is not a wall keeping you confined, It's the foundation supporting everything you experience, everything you are, everything that makes your journey through space-time meaningful. If you made it this far, subscribe and give a thumbs up. And if this exploration of physics' ultimate speed limit fascinated you, check out my video on What If You Could Travel Through a Black Hole, where we explore another boundary where physics breaks down in spectacular ways. I'm certain you'll love it. Right now, while you're watching this, particles are racing through your body at near light speed, experiencing time dilation, length contraction, and mass increase. They're touching the boundary you never will, living at the edge of possibility. And in their impossible journey, they reveal the profound truth that some boundaries exist not to limit us, but to make the universe possible at all.